Imagine a world where vast distances shrink dramatically. Consider flying from Beijing to New York in merely 2 hours. This remarkable possibility is moving closer to reality. Chinese researchers are developing a new type of hypersonic engine. This engine could redefine the future of air travel, ushering in an age of unprecedented speed and efficiency. The dream of hypersonic flight, flying at speeds greater than Mach 5, is becoming a reality. Recent developments suggest that these technological hurdles are being overcome. A Chinese aerospace company has unveiled a cutting-edge detonation ramjet engine. This engine is designed for hypersonic speeds, potentially revolutionizing both civilian and military aviation. The engine, still in its experimental phases, could make intercontinental flights as common as domestic trips. It could also provide a significant military advantage to nations that master this technology. The successful development of such an engine would place its creators at the forefront of aerospace innovation. The journey towards 2-hour transcontinental flights is just beginning. Yet, the advancements being made are undeniably exciting and transformative. This new engine technology from China is a key part of this unfolding story. It holds the potential to shrink our world in ways previously confined to science fiction. As research progresses, the dream of routine hypersonic travel inches closer. The implications are vast, touching everything from global business and tourism to international security. At the heart of this potential revolution is the detonation ramjet engine. This advanced propulsion system operates on principles significantly different from conventional jet engines. Traditional engines use a process called deflagration, a relatively slow, continuous burn of fuel. In contrast, the detonation ramjet harnesses the power of detonation waves, controlled explosions. These waves compress and ignite the fuel-air mixture with incredible speed and intensity, generating immense thrust. The core mechanism involves air entering the engine at hypersonic speeds. The detonation ramjet introduces a more violent and rapid energy release. The incoming air is compressed by the shock waves produced by the detonations. This rapid compression and subsequent ignition of fuel occur in incredibly short timescales. This process allows the engine to function effectively in the challenging environment of hypersonic flight. The detonation ramjet promises more robust and powerful performance. If perfected, this technology could unlock sustained flight at speeds exceeding Mach 5. Understanding the detonation ramjet requires a closer look at the science of detonation itself. A detonation is a supersonic combustion process. This means the combustion wave travels faster than the speed of sound through the unburned fuel-air mixture. The supersonic nature of the detonation wave leads to an almost instantaneous increase in pressure, temperature, and density. The detonation wave compresses the fuel-air mixture ahead of it before igniting it. This self-compression mechanism is highly efficient, especially at hypersonic speeds. By harnessing these controlled recurring explosions, the engine can generate continuous thrust. Chinese researchers have reportedly made breakthroughs in sustaining these oblique detonation waves using standard jet fuels like RP-3. Achieving stable and controlled detonation within an engine is a formidable challenge. The efficiency gains from detonation-based combustion are substantial. This translates to higher fuel efficiency and greater power output for a given engine size. When comparing detonation ramjets to traditional jet engines, the differences are stark. Traditional jet engines rely on rotating compressor blades to draw in and compress air. This system is highly effective for subsonic and low supersonic speeds, but faces limitations at higher velocities. As aircraft approach hypersonic speeds, conventional jet engines become increasingly inefficient. Ramjets and scramjets were developed to address these issues. However, even scramjets have operational limits and combustion stability challenges. The detonation ramjet represents a further evolution, aiming to overcome these limitations. Instead of continuous, slower burning, it uses rapid detonation waves. This allows for much faster energy release and potentially higher thermal efficiency. The intense pressure waves generated by detonations can achieve very high compression ratios without mechanical parts. This method is also thought to be more robust at extreme speeds. The advent of a viable detonation ramjet engine could herald a new golden age for commercial aviation. Imagine boarding a flight in Shanghai and arriving in London in just a few hours. This dramatic reduction in travel time would fundamentally alter the landscape of international business and tourism. Face-to-face meetings across continents could become far more feasible. Leisure travelers could explore distant corners of the world with unprecedented ease. The economic implications of such ultra-fast intercontinental travel are profound. Industries reliant on rapid logistics could see transformative benefits. The ability to connect major economic hubs in a fraction of the current time could stimulate new trade routes and business models. While the initial cost of hypersonic travel would likely be high, widespread adoption could eventually make it more accessible. This could lead to a significant redistribution of global economic activity. The dream of 2-hour flights between major world cities is now a tangible goal pursued by leading aerospace engineers. Beyond its potential to revolutionize commercial air travel, the development of the detonation ramjet engine carries profound military implications. The ability to achieve and sustain hypersonic speeds offers a significant strategic advantage in modern warfare. Aircraft and missiles powered by such engines could reach targets much faster than current systems. This speed also makes them incredibly difficult to detect, track, and intercept. Hypersonic weapons could enable rapid, long-range precision strikes. These standoff capabilities would allow attacking forces to engage high-value targets from greater distances. The increased velocity also imparts greater kinetic energy upon impact. China has already made notable progress in hypersonic missile technology. The new engine technology could further enhance the speed, range, and lethality of future generations of such weapons. The strategic balance could be significantly altered by the widespread deployment of hypersonic systems. Nations possessing this technology would gain a distinct edge in offensive capabilities and power projection. The development of the detonation ramjet engine is not an isolated scientific endeavor for China. It forms a crucial part of a broader national strategy aimed at achieving global leadership in aerospace and high-speed propulsion technologies. For decades, China has systematically invested in research, infrastructure, and talent development within its aerospace sector. The goal is to challenge the long-standing dominance of established aerospace powers like the United States and Europe. This strategic push is evident in various national plans and initiatives that prioritize aerospace as a key industry for future economic growth and national security. State-owned enterprises are heavily involved in the research, development, and manufacturing of a wide array of aerospace systems. The focus on hypersonic technology underscores China's intent to leapfrog existing capabilities. The pursuit of hypersonic engines like the detonation ramjet aligns with China's long-term military modernization goals. Mastering such technology would provide the People's Liberation Army with enhanced power projection capabilities. Hypersonic weapons could hold distant targets at risk, potentially deterring foreign intervention in regional disputes. This technological advancement is seen as a critical enabler for China to assert its influence on the global stage. While the promise of China's detonation ramjet engine is immense, the journey from experimental breakthrough to operational reality is fraught with challenges. Developing an engine that can reliably sustain controlled detonations at hypersonic speeds requires overcoming extreme conditions. Thermal management is a primary concern. The intense heat generated by hypersonic airflow and detonation combustion can exceed the tolerance of most existing materials. Therefore, advancements in high-temperature alloys, ceramic composites, and innovative cooling systems are essential. Aerodynamic stability and control of an aircraft flying at Mach 5 or higher also present formidable difficulties. The transition between different speed regimes requires sophisticated flight control systems and adaptable airframe designs. Ensuring the engine operates efficiently and stably across this wide range of conditions is a complex task. The development of such advanced technology is not happening in a vacuum. There is intense global competition in the field of hypersonic research. Major powers, including the United States and Russia, are also investing heavily in their own hypersonic programs. The progress made by China accelerates this competition and puts pressure on other countries to advance their own capabilities. The successful maturation of China's detonation ramjet engine technology stands to reshape our world in fundamental ways. Its impact will be felt across global travel, international commerce, and geopolitical security. The prospect of 2-hour intercontinental flights could redefine our perception of distance and time. Businesses could operate with greater agility, supply chains could become more responsive, and personal travel could reach new levels of convenience. However, this technological leap also introduces new complexities and potential disruptions. In the realm of defense, the proliferation of hypersonic capabilities could destabilize existing security architectures. The speed and elusiveness of hypersonic weapons challenge current missile defense systems. Nations will need to adapt their defense postures and invest in countermeasures. The broader economic impacts could also be significant. The development and manufacturing of hypersonic aircraft and related systems will create new industries and job opportunities. Ultimately, China's hypersonic engine breakthrough is more than just an engineering marvel. It is a harbinger of transformative change. As we stand at the cusp of a new technological era, the future of hypersonic technology promises even more groundbreaking advancements. Researchers around the globe are already exploring next-generation propulsion systems that could make today's hypersonic speed seem pedestrian. Concepts like air-breathing scramjets and advanced detonation engines are being pushed to their limits, aiming for sustained speeds that could revolutionize space travel and beyond. Imagine a world where hypersonic airliners make suborbital hops between continents in under an hour, or where space tourism becomes a routine part of human experience. The possibilities extend far beyond the Earth's atmosphere, with potential applications in rapid satellite deployment and even interplanetary travel. However, these advancements won't come without challenges. Engineers and scientists must overcome significant technical hurdles, including thermal management, material science, and propulsion efficiency. But with each breakthrough, we edge closer to a future where the boundaries of speed and distance are redefined. The race is on, not just among nations, but within the scientific community, to unlock the full potential of hypersonic technology. The innovations of tomorrow could very well be the keys to humanity's next great leap forward. As we accelerate towards a hypersonic future, it's crucial to pause and consider the ethical and environmental implications of this groundbreaking technology. The promise of ultra-fast travel and advanced military capabilities brings with it a host of challenges that cannot be ignored. Environmental concerns loom large. Hypersonic vehicles, especially those powered by advanced propulsion systems, can generate significant emissions and noise pollution. The impact on the Earth's atmosphere and ecosystems must be carefully studied and mitigated. Engineers and policymakers face the daunting task of balancing technological advancement with environmental stewardship. Ethical questions also arise. The military applications of hypersonic technology could potentially destabilize global security, leading to an arms race with unforeseen consequences. The accessibility of hypersonic travel raises issues of equity and justice. Will this technology be available to all, or only to those who can afford it? Moreover, the rapid pace of development necessitates robust regulatory frameworks to ensure safety and fairness. International cooperation and dialogue will be essential in navigating the complex landscape of hypersonic innovation. As we forge ahead, let us remember that with great power comes great responsibility. The choices we make today will shape the world of tomorrow. By addressing these ethical and environmental considerations, we can pave the way for a future where hypersonic technology benefits all of humanity.